Okay, welcome everyone. Does this work?
Hello, yeah, okay, welcome everyone to another AstroAI lunch talk. It is my absolute pleasure to introduce Ethan Tregidga. So Ethan was here as in the Southampton exchange program that we have. So he was here a year ago, last year. Okay, year and a half ago until 1 year ago.
Sorry, turn on.
And he did fantastic work that he's gonna be talking about today. So that was, he was a master's student with Southampton and doing his master's thesis here. Then he moved to doing his PhD in EPFL in Switzerland. And now we have the luxury of having Ethan again for the summer. So yeah, take it away, Ethan.
Thank you. So I might be doing a bit of a two-part talk sort of thing. So I'll present the main talk first, and then there's a bit of extra I can present afterwards. So I'm presenting my.
Can you switch to the?
Is the microphone long thing?
Yeah, can you? It's your computer right now.
It says the meeting now
For video too.
for videos. For video. I see what you're saying.
There.
Meeting now. There we go. Hopefully that's cool.
Sorry.
Okay, cool. That's okay now. Yes, so I'm presenting the research I did when I was back here a year and a half ago for my master's on using machine learning, or specifically autoencoders, to be able to predict the spectral parameters of black hole X-ray binaries. And this was in collaboration with Jack and Cecilia as part of AstroAI when I was back with University of Southampton. So for starters, just a brief overview of black hole X-ray binaries. So these are essentially binary systems where we have some companion normal star that is accreting its material onto some compact object such as a black hole, and that's why you get black hole X-ray binaries. And therefore these are very bright in the X-ray spectra because of how compact the objects are, and therefore they've got this accretion disk and can have these jets or other features. So for kind of just to orientate yourself to see what actually the data looks like. So this is an example of what a spectrum could look like for a black hole X-ray binary. And so there are three main components. So you have the black body thermal component, which comes from the accretion disk, and that's shown in yellow. You have the power law component, which comes from this hot corona, which the shape's questionable, but it's somewhere near the inner region of the black hole, like just around the black hole. And that is these hot electrons that when the thermal photons hit this corona, they can get constant upscatters, and therefore this will produce your power law blue component. And then finally, you can have this reprocessing effect where these now quantized photons can then reflect back off the accretion disk, and this can give, for example, some humps that at higher energies, and can also produce these fluorescence in the accretion disk, such as your iron K alpha emission lines, which will be a very prominent peak at 6.4 kiloelectron volts. So why is it useful to look at black hole X-ray binaries? So one of the uses from them is the fact that general relativity says that black hole X-ray binary, black holes have two properties, the mass and the spin. And so if you can probe both the mass and spin, you can therefore test if general relativity is accurate in these extreme gravitational regions. And so one of the ways, the mass is more easy to obtain, but the spin is one of the methods that's got some difficulties. And so that's one method you can use spectral fitting for. And so if we look at this iron K alpha emission line, we see that Newtonian from just, you will get your two peaks just from the motion, and then you, from special relativity, you will then get a boosting in one of the directions. And then finally, general relativity will then add a third effect onto this, which is your gravitational reddening, which then ends up with this line profile that, if you can accurately measure it, you can therefore, based on the spin of the black hole, you will cause this reddening, and therefore you can therefore measure the spin from this line profile. But this requires your high resolution spectra, which we'll get into next on why it's difficult. So traditionally, methods use this iterative curve fitting approaches, which are very brute force and slow. And so as you increase your model complexity or data complexity, this will become computationally very expensive. And so in this era of big data and new X-ray instruments that have 1 EV resolution, how can we improve this? And this is where machine learning can come in, which is thanks to the massive advancements in the computer science industry, and also the fact that machine learning is very highly parallelized, so they benefit a lot from graphics processing units. They can maybe, and also offer a new approach where instead of trying to iteratively improve your fit, you can instead look at a spectra, look at its features, and try to predict the parameters directly from it, similar to how a human will look at the spectrum and go, that's a black body with roughly this temperature, without having to iteratively improve your black body until you get a good fit. So we're using a very simple proof of concept model just to test if this method works. So we've got 5 free parameters. So we've got 2 multi-temperature black body parameters, that's like your temperature and your normalization of the black body component. There's 2 power law components, so that's your gamma, and the scattering fractions, that's just how many of your photons are getting scattered off the hot corona. That's your blue component. And then finally, there's the hydrogen column density, which is just your absorption of it. And we have 10,000 X-ray observations from the Neutron Star Interior Composition Explorer, or NISA. And the data set we've already got fitted using traditional methods just to get a ground truth best fit. So how do we actually go about predicting these parameters? So in machine learning, we've got autoencoders that are very useful for compressing data. So you can kind of think of this as a more fancy PCA. So the way they work is they'll take some high dimensional input, so in our case, the spectra, they will compress it to a low dimensional latent space. And the goal is to try to reconstruct your input spectra from this low dimensional latent space. So this means that the features you learn in this latent space will be the most important features, similar to your PCA components. And therefore, you can do this all unsupervised, so you don't need to have any training labels, and because all you're doing is trying to compare your output to your input. Now, this sounds great and sounds like if we encode this latent space to be our spectral parameters, then the job is done. However, a big problem with traditional autoencoders is that the latent space is non-physical, similar to PCA. It's just whatever it learns is the most important. So how do we actually get this latent space to be physical? So this is where we break up the training step into two processes. The first is to try to train the decoder. So this is going from our low dimensional latent space to our output, so the spectrum. And if we can get this to emulate our model, so this is essentially going from our spectral parameters to our spectra, so it's emulating the model. Can we train this, for example, on the model or on synthetic spectra? So we can very easily generate hundreds of thousands of synthetic spectra that have the true parameters, and then we just train this decoder to produce spectra from these parameters. So we're just emulating the model for now, and this will save us the computational cost of having to load all the data into like something like XSpec and loading all the response files and all these things. So once we've got this trained decoder, it's very good at emulating the model. We can now go to the encoder, and this is ultimately what we want. We want the encoder that goes from a spectrum to the parameters. So because we've now fixed this decoder, in order to produce a good spectrum, you need to have the right parameters. So if we train this in an unsupervised way, where we're going, like we saw with the autoencoder before, we're going from our input spectrum to our output spectrum, the encoder must learn to predict a good parameter that the decoder knows how to make into a spectrum, an accurate spectrum. So therefore, we're able to train this encoder on the real spectrum. So essentially, you can think of it as it's just learning to fit the model to the data, to the real data. So therefore, when you give it new real data, it knows what to expect and is able to accurately predict these parameters. So there's a lot here, but just to say that this is the encoder's architecture, and the main thing is to look at is the different colors. So blue is your convolutional layers, and these are, so I should say that this part is the encoder, and this is the decoder. So right here is our parameters. And so the blue ones are your convolution, which is a way to learn spatial features. And it's like sliding this kernel over the input that will just look for different features, like is it a sharp increase, is it like a long power law like component? So that's really good for the encoding as it learns these features. And then we've got these pink things that are just essentially a way to translate from these learned spatial features into the actual parameters. And then the inverse is, again, doing the exact opposite. So we take these features, we'll translate it into some features, and then we use this recurrent neural network, which is a way of learning sequential relationships. So the reason that this is useful in the decoder is that it's going to be able to progressively build up the spectrum, like increasing energy and then also backwards. And so we found that this is the best for the reconstructions, as it can learn from previous energies what the next energy should be, like when you're forming a sentence. So how do we actually come up with this architecture? So we tried several methods. So you can see there's different boxes. The red box, the red dash box is always used, and that's what we call our FNN, or the fully connected neural network. And this is just your basic, no special features network. And you can see it's very fast. It's the seconds per epoch is 0.4 for our training data. And but if we look at its mean squared error, so you can think of as how good does it actually perform. Out of all of the methods, it performs the worst. Unsurprisingly, it's the simplest and easiest. Now, if we add in our convolutional layers, the blue ones, that's our CNN, and you see, oh, it's done a lot better, but it's also a lot more computationally expensive. Whereas if we compare our yellow layers or recurrent layers, that does equivalently, but is significantly, equivalent speed, but significantly better. And so lower is better. So ultimately, this shows that the recurrent is best for reconstruction, as I was mentioning before, and then we found the opposite for encoding, which is where convolution does the best. So now if we start delving into how do we actually get this to train, we're going to look at how can we design a loss function, so that's your objective. So we can either we can test the reconstruction loss, so that's our autoencoder, how we're going to reconstruct our spectra. We can compare how well does it actually predict the parameters in a mean squared sense. And then finally, ultimately, how well does it actually fit the data? And that's what the reduced PG set is. So we're using PG Poisson, assuming our data is Poisson distributed and the errors are Gaussian distributed. We're using these statistics as the ultimate goal, and that's what we really want to get down to. Ideally 1, but you're not going to get 1 with this model because the model's basic in approximation, and then anything higher is starting to get worse. So that's ultimately what we want to minimize. And you can see that if we just do a supervised loss, yes, sorry.
Yes, one question, please.
Yeah.
As you use PG stats, does this mean? Okay. Yeah, as you use PG stats, does that mean that you have a separate model for the background, or is it included in your forward modeling procedure?
To model the background data, the background noise.
So this just goes in as an independent measurement.
Yes. So to model the background, I can't remember the exact background model, but we have all our background files that we will subtract from all data. So when we do our data normalization, we subtract the background model. If that
Okay, so it's subtracted before you go into it.
Yes,
Okay.
yeah, it's all in pre-processing, yes. Yes, so if we compare the reconstruction loss for the supervised case, so the supervised is where we are just training the encoder on our data. So it's just going to use a mean squared error loss on the predicted parameters, and just going, how well can you predict parameters? And so unsurprisingly, it does the best when you compare it to the parameter mean squared error compared to all the other methods. The unsupervised one is when we just have the autoencoder structure. So we do our decoder trained first on to emulate the model. That's how we can physicalize the latent space. But then when we train the encoder, we do that in an unsupervised way, like I was mentioning before, where we just train it to compare the output to the input. And in the semi-supervised case is when we combine these two loss functions so that we have the reconstruction loss and we've got a mean squared error loss on the latent space to compare to the parameters. And so we can see that, unsurprisingly, unsupervised, when it's trained on the reconstruction loss, does the best. The supervised does the best when it's trained on the parameters. And the semi-supervised is pretty good on both of them. And so then when we actually look to the final reduced PG stat, we see that actually the semi-supervised does the best. And it even beats the supervised does significantly worse, and the unsupervised is actually pretty close to the semi-supervised case. So why does that make sense? You kind of think that's, if it's directly trained on the parameters in the supervised case, that may perform the best. Well, if we start looking to some of the figures, you can see that this is for example, just one of the parameters. You can see in the supervised case, it does a very good job at predicting the parameters. It's very close to being on, if this is the predictors and that's the true, it's very close to being 1-on-1. Whereas if you look at the unsupervised, it's completely unable to predict the parameters. So you think that should be a really good thing. But the problem is that if you have, let's say we've got two parameters that control the scale of your spectra. If you're just trying to minimize the mean squared error, you could say both of these parameters could slightly underpredict the parameter, and therefore they'll have a small mean squared error. But if you then combine these two underpredictions, then the resulting spectrum can be significantly underpredicted because they're both scaling down. Whereas if you do the unsupervised case, it's forcing the parameters to be able to accurately reconstruct your spectrum. And so therefore, if one's slightly underpredicted, then another parameter for the scale has to slightly overpredict to compensate for that. So therefore you get a more realistic reconstruction. And the semi-supervised case can therefore fix problems like this. So now you see it gets back on track for these difficult parameters, but is also able to compensate for these scaling problems. You also notice that, for example, we'll take another parameter. These are the distributions. So the blue is the target and the yellow is the predicted parameters. And you can see that for the supervised case, it looks very good. And if you look to the unsupervised, this is the scatter fraction. So this is a fraction, so it should be between 0 and 1. Well, you see that this is 1, and the network's predicting up to 100. So you can see in the unsupervised case, it doesn't have a concept of what's physical, and so therefore it's happy to just predict unphysical values. And so you can it's found a region in the decoder to reconstruct a good spectrum. It's found a region outside the trained parameter space that actually still produces a good reconstruction. But as soon as we add the semi-supervised loss, it then mostly fixes this problem again, similar to the supervised case. So this shows that if you have a small subset of your observational data that you've already pre-fitted, you could improve the performance by training on this using the semi-supervised approach. Now, if we look at, so after we've trained our network, we want to get all our predictions, we can therefore compare all our predictions. And these are kind of the final predictions for our toy model. And you can see that it does very good for the hydrogen column density, and it does pretty good for the disk black body components. So that's your temperature disk, and that's your normalization. The gamma and the scatter fraction for the power law component generally do quite well, but you can notice these very unphysical vertical regions that look very anomalous. And these are essentially where we're comparing the ground truth that we did in traditional fitting against network predictions. So what happens is if the traditional fitting hits one of the limits, and while it's fitting, it will then get pegged at this limit and won't change after that. So what we are potentially seeing here is that while traditional fitting may get stuck in, for example, a local minimum, and then get stuck at some limit, the machine learning won't have the same problem because it's not doing this iterative fitting. So therefore, it could be a way of getting around local minima in traditional fitting, as it doesn't have to worry about these pegged limits. And you can kind of see that the red points is where one of the parameters has been pegged. And so you can generally see that the points that are doing the worst are generally more red, and therefore it's less reliable for the network to train on. Okay, so now a big problem with machine learning is people go, oh, it's a black box function. How do you know what it's actually learning? And this is one of the ways to try to figure out more what it's learning. So this is saliency. This is essentially just going, how much does the input affect the output of the network? And so what we can look at is if we bin this, so essentially we'll produce a saliency value for each point in the spectrum. So what we do is we just bin it up to get a more clear overview. And what we see is that these three are more soft spectra. So you can see the peak of the spectrum is at lower energies and it's more black body dominated. Whereas this one here is a bit harder. It has the peaks more shifted to the right and has more high energy components. And so if we look at these soft ones first, we see that all three of them show a significant importance placed around the beginning of the spectrum and generally around the transition point where you go from the black body to the power law component. And then potentially there's also a focus later down here, which maybe is the network learning on how to constrain the lines. It's kind of like taking 2 points in the line, just fitting between them. Then if we look to the higher spectrum, you can see it's more evenly distributed. We still see this early peak, which maybe traces the rise in the spectrum. We trace, maybe this is a transition point, and we trace more thoroughly throughout the power law component as that's more important. So now if we actually get onto the final results, we can see these are the final reconstructions, and you can see it does a pretty good job. So this is on real data. You pass in your input spectrum, goes through your autoencoder, and this is your decoder's reconstruction. If you see that straight line, that's just a problem of logarithmic space. And so if you have any values that are 0 or negative, then I've just to make machine learning happy, I've just fixed that at the minimum value. So that's why you get this weird straight line. So now if we go to our real data, we compare several scenarios. So we've got just the encoder's predictions. How does that compare in the PG statistics? We've got brute force fitting. How does traditional methods compare? And then we've got the encoder's predictions. If we use them as the initial starting point and then do traditional fitting on top of that. So can machine learning get you closer to the answer, even if it can't quite give you the best answer yet? So this is the final results table. So we see that we've got the fitting time for 1,000 spectra, and you've got the reduced PG stats, which is the median value for that 1,000 spectra. So you see that the encoder takes 36 milliseconds, whereas traditional fitting takes about 98 seconds to achieve a similar reduced PG stat. So you can see that that's a significant improvement, about 2,700 times faster. However, if the best fit is about 4, that's quite far from the best fit still. So how can we take our encoder's predictions, do fitting, how much do we need to do to get to the best fit? So if we do the encoder's predictions plus 10 iterations of fitting on top of that, we can get to 4.76, so close to the best fit, and that'll take you about 96 seconds. However, if you then compare that to traditional fitting, this now takes you 290 seconds as it takes 60 fitting iterations, which is rather interesting because if 10 iterations gets you equivalent, then you think 10 more would get you the best fit. So this suggests that in the fitting algorithm, it's either getting confused with local minima, or it's just slowing down its convergence. And therefore, by giving you the encoder's initial predictions, you can get much more quickly achieve the best fit than without it. So what this I would expect is, as you go to a more complex model, and where these computational, these fitting times become significantly longer, then the closer you can get to the best answer with machine learning, then you're going to be significantly reducing the computational time, as the machine learning won't necessarily, it will negligibly scale with model complexity, assuming you don't need to have a whole new model. And so, in summary of the first project, we've shown that we can rapidly predict spectral parameters, and not yet at best fit, but we can get most of the way there. And then we are able to emulate, as a side effect of the decoder, we're able to reconstruct the spectrum. However, so the main problems, I think, with this model is the fact that we have to train in logarithmic space, because if the spectra is scaling several orders of magnitude, that causes computational problems for machine learning. The problem is if you go to logarithmic space, you're now placing more importance on the low counts part of the spectra, and if you're slightly wrong in logarithmic space on the peak, so let's say you're a few points off, then if you go to linear space, you could be significantly off. So if we can get this network to learn in linear space, then I think that will massively help with our accuracy. And then also we'd like to then go to more complex models. So we're currently working with Andre on this more complex 20 parameter model. And so we're going to see if we can adapt this, and also as well as include uncertainties in our predictions, because right now we're just predicting a single value. But can we, it'd be it's very easy to get the uncertainty of the network, but can you actually get a prediction for the uncertainty of the parameter? And so there's some methods we're going to explore with this. And yeah, so normalizing flows is one example. Now, if I have enough time.
Yeah, you do, but should we do like questions
Yes,
about
yeah,
this
we can do questions
first?
first,
And
yeah.
the rest is work in progress, so maybe we
Yeah.
stop the recording.
Yeah, okay.
Yeah, okay.
Okay, any questions about this part of the talk? Yeah, okay. Everybody.
I think you're alluding to this with the log transform.
Yeah.
But I mean, the normalization is a funny parameter.
Yeah.
And you didn't list that as one of the parameters being fit. So when you're fitting, are you normalizing your data before going through the encoder in some way?
Yes, so we normalize all the data to scale. So we take log of all the data first, and then we scale them all between 0 and 1. So the most maximum, the global minute 0 and 1. So the most maximum spectrum, we take as the maximum, and the most minimum value out of all the spectrum, so typically 0 is the minimum, and we just scale them all like that. So they all fall somewhere between 0 and 1. You can see that here. So it's a 0.4 or whatever. So yes, that is and that means when you give it new data, you have to apply the same transformation. Yeah.
Thank you, and nice.
Thank you.
So one could naively think that the way you train your autoencoder would be useful for two purposes. One would be what you're doing, trying to recover spectral parameters.
Yeah.
The other one would be just the decoder.
Yeah.
However, the autoencoder is not variational, so I guess
Yeah.
the space that the latent space is not connected makes it difficult to do it. However, you're also training with using in the loss function a combination of the mean square error and the reconstruction error.
Yeah.
I wonder if that compensates for the fact that the latent space is not connected. In other words, if you just pass parameters to the decoder and get reconstructed spectra for values that were not in the training set, do you still get a good recovery of the spectrum? That's my first question. Second question is, are you actually considering to turn this into a variational autoencoder, or just go straight to the normalizing flows, because it sounds like it might be just better, you know?
So the first question was if I give it new values for the parameters that's not been trained on.
Right, if you just do the decoding part.
Yeah.
Is the reconstruction as good as just running the simulation with those parameters?
Like expect.
Oh, like
Right.
Yeah, is the emulator good enough?
Can you use it as a generator? That's kind of my question.
yes, you can use it as a generator. It will. I suppose I should just go back here. It will generate a perfect model because it's all been trained on. So it won't give you INK alpha lines, for example, because it's not been trained on that. But yes, you can really use this. And one idea is, could you just use the decoder and do traditional fitting using this accelerated decoder, and therefore converge faster? And I don't know if I just changed it.
Yeah, I'll ask
Okay.
you later. Maybe my question doesn't make
yeah.
sense.
And then in terms of variational autoencoders, yes, we did think about that. It might be useful just to test, see how well it works. I've had problems training variational autoencoders before, so we'll see. But I think a normalizing flow, because it predicts a distribution, it might be more useful rather than just predicting a mean and standard deviation. So for people, variational autoencoder is just a way of, instead of predicting a single value, you predict the mean and standard deviation in your sample from that. Whereas a normalizing flow, you're trying to learn this transformation to go from a Gaussian to this complex distribution, and therefore you can get a more rich distribution, and hopefully that will accurately tell you, like, for example, how well parameters couple and these things. But I think what you're saying before with the by adding these two losses and how they can kind of learn to couple parameters together, I think it's exactly what we're seeing here with the supervised versus the unsupervised and the semi-supervised, is that the supervised, it just fails on the reduced PG stat because it's all parameters are independent. Whereas if we do the unsupervised, we see that it can fail on some parameters and just compensate for other parameters. So by doing a combination of the two, you can therefore make sure that all parameters are trying to be accurately reproduced.
Thank you so much. Great talk. So I think maybe 3 questions. So the first one is regarding the internal structure of these spectra. So did you look at the PCA, just taking a look at all the spectra, because these spectra, the first order bunch of black body spectra, different temperature, superposition. So is it useful to first do a decomposition in eigenspectra and then use, for example, autoencoders to train the residual? Might be a little bit of an easier problem.
Yes, that is a good idea. And when I was wrapping this project up, we, I think in the reports, on the reviewers' reports, they were mentioning some other research that was similar. And a lot of that was using PCA either just as is, or even as an initial condition, like you were saying, for the machine learning. And in one of my, the next thing I was going to talk about, the next work I'm going to talk about, I was looking potentially into that area. And so I think it could be very useful, and they found generally good success with it. So that could be another way just to help with this problem, and maybe especially if the scaling problem, that will help that.
Yeah. And so the next one is, so if I understand correctly, you are using essentially the maximum likelihood estimates, traditional fitting as a training set.
Yeah. The
issue that you might encounter here is, so maximum likelihood is quite sensitive to model misspecification, meaning that if your model is not, if the true model is not in your model set, parameter estimates tend to be quite far off.
Right.
So one thing that, so I'm, for example, interested in robust regression techniques, linear valuing. One thing that you can do is you don't have to use maximum likelihood, right? So because that's related to the distance between distributions. In this case, with a guideline, you can use other distances that are a little bit more robust. So one thing that you could also try is just view the traditional fitting technique as a simulator, right? So you can simulate mock spectra.
Yeah.
You have mock spectra and you have measured spectra, and you build an emulator on that simulated data set directly.
Yeah.
That might be useful. Then you can use other types of distances like maximum mean discrepancy that are a little bit more robust against model misspecification errors. That might be
right. So you're saying to so in this training step, you train this whole thing on synthetic spectra.
So the first thing that you could do is, this is all like known emulator theory statistics. So one thing, so first of all, you have to think about what's the emulator design.
Yeah.
So Latin hypercube, for example. So you have a bunch of parameters that describe the simulation.
Yeah.
And you essentially design a high-dimensional grid.
Yeah.
Where you can adjust the grid spacing. If you put these points closer together, you have better reconstruction.
Yeah.
Further apart, you need to interpolate more. So then on each of these points, right, you generate your mock spectra, the simulator.
Yeah.
Then you have simulated spectra. What you then also have is, so there's no noise there.
Yes. Yeah.
But you will have measured spectra that you would like to include in this in the filling of the emulator. So at the end of the day, you have two different types of data. So you have the simulated data, and you have, for parts of that cube, you have also measured data. And then you write down, you fit your model, whoever it is, so whatever it is, like a linear combination of PCA plus like a generative model or some sort of Gaussian process on that combined data set.
Yeah,
So that might be
Yeah.
a way to improve it.
yeah, it'd be useful, yeah.
Yeah, because then typically you use the measured data as a calibration source.
Yes.
So in the regions where your mock data, your mock simulations are less accurate, you can use this measured
I see,
data, right, to
yes.
refine it. And that's the way you beat down essentially modeling specification error and emulator design.
Right.
And there is a whole theory in statistics about how to design these emulators. So one thing that you will not know in advance how good the emulation is.
Yeah.
So you will not know in advance how thinly spaced your hypercube has to be. But there are certain designs that allow you to, after you find out that in certain regions you are not good enough, you can, after the fact, you can make this grid spacing thinner.
See, yeah.
So this is I can send you a couple of
Yeah, that'd be very useful.
papers from the
I
statistics.
think this would be good for another
Yeah.
meeting, like a
Yes, yeah.
separate meeting. But I think we have to move on.
We have one question online,
Okay, sure.
so go ahead.
Yeah, so this is a very specific work, it's specific to NICER data. What's gonna happen if you go to any other missions alone or in combination over different energy ranges? The spectral are gonna look different. The model is gonna be essentially different. Won't you have to go back to the beginning for each and every such case?
Yes, that's a good question. So ultimately, yes, what you could do is you could train the network itself. There's several different domain adaptation techniques, but you could, for example, train it. So the decoder is just trained on synthetic spectra. So for multiple instruments, you can either train multiple encoders when you're training multiple encoders, or you just train it, you give it multiple instruments during training, so then hopefully it becomes more insensitive to the instrument itself. But for different models itself, what you could do is, if the models are in some way additive or easily implemented, you could train a network, a different decoder for each model component. So maybe there's a decoder for the blackbody spectrum, there's a decoder for the power law, and then you can go, if I think it's both a blackbody and a power law, I can then combine these two decoders. If there's more complex relationships, so we're using the simple cut method, which then convolves the power law with the blackbody, then maybe you could have a blackbody predictor and a power law predictor, and then you could have another predictor on top of that will then take these predictions and then mix them together. But yes, you're right that depending on the instrument used and the model used, there's several different training techniques, but hopefully either you have enough data that it's still combinationally more cheap than it is to do traditional fitting.
Can I add something to that? So I have to say that Ethan's model has been very easily adapted to completely different problems. So one thing is the data you use to train and the problem you want to solve. Definitely different instruments will need maybe transfer learning or some kind of work. But what takes the most time of a project like this is if you look at the architecture, what Ethan was showing, how many layers of this kind, just recurrent help. And this architecture, we have used it for exoplanet, for biomarkers in exoplanet atmospheres, and we had a model that was really performing really well in 2 weeks rather than in the whole 10 months that took Ethan to do this. And we're using it for cosmology and for the Earth atmosphere. So I think there's a lot of transferability regardless of the particular data you want to use. The value, a lot of the value is in, okay, we do have an autoencoder that now we can extract physical parameters for the first time. Okay, so maybe let's move on to the second part of the talk, and we're gonna not record this because it's working.